and let's share the screen. Okay, and yes, so and any questions, comments, suggestions? Okay, all right. So if there are no further questions, then we will go ahead. So last time we saw the concept of connectedness. We will come back to this topic of connectedness once we have a good understanding of continuous function. So towards that goal, let us start with understanding what is the meaning of a function to have a limit. Yeah. So I think this is lecture number 20. So if you look at the book by Bartley and Shepard, then we are back to chapter 4 of limits after a brief digression to chapter 11, which was a glimpse into topology. Yeah. Okay. So as I said, the plan for the day is to understand what is the meaning for a function to have a limit. Okay. So can you see the screen, lecture 20 on your at your end?
Yes, ma'am.
Okay, excellent. All right. So the very first definition. So I believe everybody here has seen limits at some point of time. So what we are going to do is define limits for a function defined between two metric spaces. Yeah. So, so suppose that x, so there are two metric spaces. So I have x dx and y dy are two metric spaces. And suppose that let E be a subset of X, and suppose that F is a function defined on E taking values in Y. All right. So let's consider a point P of X, which is a limit point of this set E. Yeah. So let P belong to X be a limit point of the set E. Yeah, please recall, this means that the point P may or may not belong to the set E. Yeah, okay. So what is it I am interested in considering? I am interested in considering the limit of the function f as we tend to P. Yeah, okay. So suppose that Q be a point in Y. Then we say that the limit of the function f(x) as x tends to P exists and equals Q provided the following is true. So if for each epsilon positive, so let me write this definition down, and I'll try to convince you that this is exactly what you are already familiar with. If for every epsilon positive, there is a delta positive such that the distance in Y between fx and q is less than epsilon whenever X is a point of E different from P, and the distance between between X and P is less than delta. Yeah. Okay. So let's see what is happening here, right? So let me try to draw a picture here. So let's say I have a function f from E to Y, yeah, and so E is sitting inside a set X. X and Y are both metric spaces. Yeah. Now P, the point P is a point of X, and P is a limit point of E. Yeah. So what are we trying to do? And Q is some point in Y. Yeah. You give me an epsilon positive, and I am going to look at the neighborhood of the epsilon neighborhood of the point Q with respect to the metric in Y. Yeah, so I am going to draw here pictures in R2. So in R2, it looks like a ball. Yeah, so assuming that Y is R2, I'm drawing this picture. Yeah. So given epsilon positive and this point Q in Y, I'm looking at the epsilon neighborhood of the point Q with respect to the metric on Y. Yeah. If I can find a positive delta such that if you look at the delta neighborhood of the point P with respect to the metric on X, which means that I look at this set, yeah. So this is a delta neighborhood of the point P. So if corresponding to this epsilon, I can find a delta such that any point X in this neighborhood of the point so any point X in this delta neighborhood of the point P lands in this epsilon neighborhood of the point X. Yeah. So this is true for every point X of this. So let me draw it in a different color. So this is true for every point of this delta neighborhood of the point P, except at the point P itself. Yeah. Now the question is, why do I leave it the point P? See, the function is defined from E to Y. So a priori, and P is a limit point of the set E. Yeah? So the point P may or may not belong to the set E. So f of P may not be defined. So there's no even, the question doesn't arise that you talk about f of P. So when do we say that the limit of the function f of x exists? We say that if each time I give you an epsilon and you manage to produce a corresponding delta such that this diagram makes sense. Yeah, what does it make sense? See, I give you an epsilon and you manage to produce a corresponding delta such that all the points X in this delta neighborhood of the point P, which is this shaded region in red, except the center point P, land in this epsilon neighborhood around the point Q via F. Yeah, that means f of x is in this epsilon neighborhood of the point P, of the point Q. Yeah. So this is, using epsilon as a measure of closeness, just as before. Yeah, we have done this many times. Yeah. So if this happens, then we say that the limit of the function f exists at the point P and equals Q. Something to be noted here, the concept of limit of a function at the point P is defined only when P is a limit point on the set E, on which the function f is defined. Okay, so is this okay with everybody present here? This definition?
Ma'am, will you please repeat?
Okay. See so I'll draw another picture. Let's say now in R. Yeah. So what is it saying in R? So this is saying you look at so E. You have a function f from E to Y. E is a subset of X. P is a limit point of E. Yeah. So P belongs to X. Surely P may or may not belong to E. So if you look at draw this picture in R. Q is some point of Y. Yeah. So you give me an epsilon positive, and I am going to look at an epsilon neighborhood of the point Q. Yeah, so which means Q plus epsilon, Q minus epsilon. If corresponding to this epsilon, so P is somewhere here in X. If corresponding to, so I'm drawing this picture assuming both X and Y are the real line with the Euclidean metric. Yeah, this is just a pictorial representation. So if corresponding to this epsilon, you can find a delta such that what happens? Such that if you look at this delta neighborhood around the point P, yeah, so this is an interval on the real line, and you pick any point in this in delta neighborhood. Yeah, so I'm denoting this point A. This any point X in this delta neighborhood of the point P is mapped via F into this epsilon neighborhood of the point Q. Yeah, and this, if this happens for every epsilon that I give you, yeah, if for every positive epsilon you manage to find a corresponding delta such that for all X in this delta neighborhood of the point P except the point P itself, they are mapped via F into an epsilon, into the epsilon neighborhood of the point Q, then we say that the limit of the function F exists and equals Q. Yeah, is that any better now?
Yes, ma'am.
Yeah, see, this is what you have already been doing. It's just that now it is written in terms of metric spaces, nothing else. Yeah, is that okay with everybody present here? Okay, so shall I take this silence as a yes? Any questions? Okay, so let me go ahead. Please don't hesitate to ask if you have a question. Something to note that. So note that the point where we are considering the limit, the point P may not belong to the set E. Yeah. Again, this is something familiar. I'll just sort of emphasize, but P certainly belongs to the set X. So something to be noted, take a note of here, that the function F may not be defined at the point P. Yeah? So for example, so I'm sure everybody is familiar with this. So example, let me consider F as a function from open interval 0 to infinity to R. Yeah. So I have Euclidean metric. So there are two metric spaces, Euclidean metric on both the sides, and let's consider a function F given as follows. So let me write, let be given by, so I'm sending the point X to sine of X by X, right? So clearly the function F is not defined at the origin, yeah, in this example. But we know that it has a limit of 1 as x tends to 0. Yeah, this is calculus, which I'll skip for the moment. Yeah, but I'll just that the limit of f as x tends to 0 exists and equals 1. So as x tends to 0. Is that okay? Or maybe, I have introduced this notation, so I'll write that in the notation that is everybody with me up till this point?
Yes, ma'am.
Okay, all right. So this limit exists and equals 1. All right. The next point is, it is very well possible that the point P belongs to the set E. Yeah. So in that case, we are saying that the limit of the function f exists and equals some point Q. Yeah? So even if P belongs to the set E, it is very well possible that the limit of the function f as we tend to the point P does not equal f of P. Yeah. So this is another thing that I would like to highlight. So again, this is something that you already know, but let's just note that one more time. So even if the point P is indeed in E, it may happen, yeah, it is possible. So both ways is possible. It is also possible that the limit of f at as we tend to P exists and equals f of P, and it is also possible that the limit of the function f as x tends to P is different from f of P. Yeah. So again, let's just sort of note it down. So here's an example to illustrate this. So let's consider f a function from R to R. So as I said before, unless stated otherwise, this is to be understood as a function from the real line with the Euclidean metric into the real line with the Euclidean metric. So let's define f as follows. I'm just going to say, so let's say f of x is going to be 0 if x is different from 0, and at the point 0, the function is defined to be 1. Yeah, so this is x equal to 0 here. And now, so the set E is the real line in this example. And now I want to consider the limit of the function f of x as x tends to 0. So what would be this limit in this example?
Zero.
It will be 0, right? But what is f of 0? It is 1. So this is different, not equal to f of 0, right? Is that okay?
Yes, ma'am.
Yeah. So, I would sort of urge you that please don't confuse this definition of the limit with limit of a sequence. When you consider limit of a sequence, you are actually looking at a function from the natural numbers into the metric space. Yeah. And the point P is replaced by the symbol infinite, right? Is that okay? Okay. But I think with this, it's a good idea to give a characterization of a limit of a function in terms of limits of sequences. Yeah. So is this, whatever we have discussed so far, is this okay with everybody present here?
Yes, ma'am.
Okay,
Yes,
excellent.
ma'am.
Excellent. All right. So let's so next is a characterization of limits, limit of a function in terms of limit of sequences. Let me write it as a theorem. So as before, we have two metric spaces. X dx and y dy. All right. And E is a subset of X, and F is a function defined on E. So F is defined from E to Y, and P is a limit point of the set E. Yeah? P is a limit point of the set E, and suppose that Q is a point in Y. So we already know what is the meaning of the statement that the limit of the function fx, so of the function f at the point P exists and equals Q. Now, what is the point of this theorem? To give a equivalent criteria in terms of sequences. Yeah, so I would say that so the limit of the function f at the point P exists and equals P. So let me just fix this. It's rather sloppy. Uh, a little better now. Yeah. Equals Q if and only if for all the sequences so I should write them by some name. For all the sequences, so let's say AN in the set E minus P. Yeah? So AN is a sequence of points in E. Each element of AN is different from P with the property that so let me be a little bit careful. Sorry, I would like to reword it a little bit. So we look at all the sequences in the set E minus P. Yeah? If and only if yeah, so as I said before, AN is a sequence of points in E. Each AN is different from P such that the limit of the sequence AN exists and equals P. Yeah. Now, what do we want? We say that if for every such sequence, you look at the corresponding sequence in Y, which means that you look at the sequence f of AN, we demand that the limit of this sequence exists as n tends to infinity and equals Q. If and when this happens, then the limit of the function f at the point P is Q. This is an if and only if criteria. Yeah, so let's sort of draw it in pictures. You look at the set E. Here is Y. You have a function. E is sitting in X. Yeah. So some point P here of X. Look at the point Q. Now you look at any sequence in the set E which is tending to the point P. So let me denote it by this. So this is a sequence of points AN. Then the corresponding sequence in Y of, so you look at the image sequence f of AN. So if the sequence AN converges to the point P, then the corresponding sequence FAN must converge to the point Q. And this should happen for every sequence in the set E minus P converging to the point P. Then the limit of the function f exists and equals Q. And likewise, right, that if the limit exists, then this is true for all sequences converging to the point P. Does everybody follow the statement of this theorem here? Yeah, is that a yes with everybody? Okay, all right. So let's fill in the proof quickly. Okay, so let's suppose that the limit of the function f at the point P exists and equals Q. Yeah? And let's assume that let us consider a sequence of points in the set E. Yeah, let me sort of write it in a different manner. So let An be a sequence of points in E. An is different from P for each n such that the sequence an converges to P as n tends to infinity. Yeah? What are we required to show? We are required to show that the image sequence f of an must converge to Q. Correct? Is that okay? Yes. But what is given to us? We are given that the limit of the function f at the point P exists and equals Q. Yeah? So by definition of the limit given any epsilon, there is a positive delta such that what happens, such that I'm going to sort of reproduce the definition here, such that the distance in y between f of x and q is less than epsilon, which means that f of x belongs to this epsilon neighborhood around the point q whenever x is a point in E different from P and x comes from delta neighborhood of the point P. Yeah, which means that the distance between x and P is at most delta. Correct? Is that okay? Just rewritten the definition here. Yeah. Now, what are we required to show? We are required to look at the sequence f of an and show that that converges to the point Q. Yeah. Okay. But let's also note the following, that we are also given that the sequence an converges to the point P, which means that that the following is true. Yeah, so let me draw a picture again for the benefit, just makes things a little more clear. Yeah, so I have a set E here. I have a function. I have a point Q. I am looking at epsilon neighborhood of the point Q, yeah, which is this shaded region. Corresponding this is epsilon. I am guaranteed existence of a delta such that if I focus on a delta neighborhood of the point P, yeah, then any x here is mapped via f into this epsilon neighborhood of P. This is true for every x in this delta neighborhood of P except the point P, where the function is not even defined. Correct? Now, what are we given? We are given that the sequence an converges to P as n tends to infinity. Yeah? Now, since the sequence an converges to the point P, we can always find a large n such that an's are inside this delta neighborhood of the point P some stage onwards. Correct? Is that okay? So I'm going to write that down. Furthermore, we can find a positive integer n such that all these ANs lie in this delta neighborhood of the point P, which means that this holds some stage onwards, and that stage is determined by the index capital N. Is that okay?
Yes, ma'am.
Yeah, is that a yes with everybody present here? Yes. Now, you just combine these inequalities with the fact that ANs are all points of E, yeah, which means that f of ANs are defined, and just apply it here. Yeah, so ANs are points in E. Each AN is different from P this is by assumption. And ANs are in this delta neighborhood of the point P. So hence this inequality tells us, the definition of the limit tells us that f of ANs must lie in epsilon neighborhood of the point Q. Yeah? So I'll just say that combining inequalities with the fact that ANs actually are points in E, and each AN is distinct from P, gives that the ANs are mapped via F into this epsilon neighborhood of the point Q some stage onwards. Correct? Now, this is exactly saying that corresponding to an epsilon positive, there exists a positive integer n such that f of ANs are in epsilon neighborhood of the point Q. Yeah? So this is exactly saying, in other words, that the limit of the sequence f of AN exists as n tends to infinity and equals Q. Is this okay?
Yes, ma'am.
Is everybody with me up till this point?
Yes, ma'am.
Yes. Okay, excellent. So now let's look at the other part of this proof, which means that suppose that for every sequence of points in E minus P, the corresponding image sequence, so every sequence of points in E minus P converging to the point P, the corresponding image sequence converges to Q. We are required to show that the limit of f at the point x at the point P exists and equals Q, right? So suppose not, right? Suppose not. So let's see. So suppose next that the limit of the function f, this does not hold true, right? So what would be the negation of the definition? So the definition says there exists an epsilon such that there exists an sorry, what am I saying? The definition says for every positive epsilon, there exists a delta such that something happens, right? I'm looking at the definition of limits here, right? So what could be the negation of this statement? Somebody help me with this, please.
Ma'am, for all epsilon greater than 0, ma'am, there exists epsilon greater than 0 such that for all delta greater than 0,
Correct.
dy fxq greater than epsilon whenever x belongs to.
Whenever, correct. Whenever, yeah, you are absolutely right. Yeah, so let me just put that down here, right? Thank you so much. Okay, so this is the negation of the definition is that there exists an epsilon positive such that for every delta positive, we have the following statement. Yeah, what is that? So the distance between fx and q is at least epsilon for some x in the set E with right. So what is this saying? Let me again, try to convince you by a picture. This is saying that so again, f is a function from e to y. E is sitting inside x. There is a point P of x and there is a point Q of y. And the limit of f at the point P does not equal Q. Yeah, which means that there is an epsilon positive such that no matter what delta I choose, yeah, so there is an epsilon positive. So let me draw an epsilon neighborhood of the point Q. So there exists an epsilon such that for every positive delta, yeah, there is some point in this delta neighborhood of the point P such that its image is outside this epsilon neighborhood of the point Q. Yeah. So this is saying there exists an epsilon such that no matter what delta I choose, I can always find a point in that neighborhood around the point P such that its image is mapped outside the epsilon neighborhood of the point Q. Is that okay? Everybody understands that this is what is the negation of the definition of the limit? See, I'm trying to draw different neighborhoods of the point P in different colors. Is that a yes with everybody?
Yes, ma'am.
Yes? Okay, all right. So what do we do? Now, what is that we are required to do? See, with this assumption, we will produce a sequence of points tending to the point P such that the image sequence f of, so let me call that sequence of points an. So we are going to construct a sequence of points an tending to the point P, each an distinct from P, such that if you look at the image sequence f of an, that does not converge to Q. That cannot happen. Yeah. So let me try to do that. Yeah. Okay. So let's fix such an epsilon as here. So let me change to black ink. Still green, doesn't matter. So let let us fix such an epsilon. So maybe I'll call it epsilon naught for the sake of definiteness. Yeah. Since yeah. So I'll say that there is an epsilon naught such that this and this picture, this is epsilon naught here. Okay. All right. So I'm going to work with epsilon naught. Now, corresponding to this epsilon naught, no matter what delta I choose, there is always a point in that delta neighborhood of the point P, which is mapped via F outside this epsilon naught neighborhood of the point Q. Yeah. So corresponding to this epsilon naught, for each delta, I'm going to take delta as 1 by n positive. Now, this guarantees me that corresponding to this epsilon naught, if I look at a 1 by n neighborhood around the point P, there is going to be a point in that neighborhood which is going to be mapped outside this epsilon naught neighborhood of Q via F. Yeah? So I'm going to say choose points an in this set E minus P with so what are ANs here? ANs, what is achieved by doing this? ANs is a sequence of points tending to P with the property ANs lie inside the set E and each AN is distinct from P by construction. Is that okay? Yeah. Now, I'm just rewriting it one more time. Now, AN is a sequence of points in E minus P such that what happens to the sequence f of AN? The sequence f of AN lies outside, all these FANs are here outside this epsilon naught neighborhood of the point Q by construction. Yeah? So clearly f of AN, the sequence f of AN does not converge to Q. Why? Because by construction, the distance between f of AN and Q is at least epsilon naught, it's positive, and we are done. Yeah, so I just write here for all n. This is true for all n. Is that okay?
Yes, ma'am.
Yes? Is that a yes with everybody present here?
Ma'am, can you say the last part once again?
See what have we achieved by all this construction? We have found a sequence an of points in E. Each an is different from P such that an tends to P, but the corresponding image sequence f of an are outside this epsilon naught neighborhood of the point Q. So that implies that the sequence f of an does not converge to the point Q.
Yes, ma'am.
Correct? Is that okay?
Yes, ma'am. Ma'am, how are we arriving at the contradiction?
Okay, so we are arriving at the contradiction because we are proving this. Yeah, so we are under the assumption that for every sequence an in E minus P, so I'll just go back to the statement of the theorem here. See, we proved that if, so the first part of the proof was if the limit of f at P exists and equals Q, then there is this sequential criteria for limits. Now we are looking at the converse part. So we are under the assumption that limit of FAN equals Q for every sequence AN of points in E such that AN tends to P. And we are required to prove that limit of f x as x tends to P exists and equals Q. So we are saying suppose not, and that's how we are progressing. So the contradiction is that here is a sequence, so maybe I should write it as something else. So the contradiction is that, so let me call it something else, yeah. So let me call these points An prime. Maybe that will help. So An prime, yeah, so this is An prime. So here I have found a sequence of points An prime. In E minus P. Let me just go back to the statement of the theorem. So I have found a sequence of points An prime in E. Each An prime is different from P. An prime converges to P such that the corresponding sequence Fan prime does not converge to Q. This is much against our assumption. Our assumption was that for every sequence An in E minus P converging to P, the corresponding image sequence Fan must converge to Q. Is that okay?
Yes, ma'am.
Yeah? All right, good. So is this okay with everybody present here? Okay, so if that is the case, we record an immediate corollary of the theorem, which says that limits are unique if they exist. Yeah, because limits of sequences are unique is what we have already seen when we were discussing sequences. Yeah, so I'll just write this corollary. The limits of a function. Yeah, so I am talking about limits of a function. Unique provided they exist. All right. So I believe everybody is with me up till this point. So much like there were laws, you know, for algebraic laws for what happens to the sum of two sequences, right? We said that limit of a sum is sum of the limit provided the limit exists. There are similar things here, and let me jot that down here for the sake of completeness. Yeah, so limits behave as expected with respect to addition and multiplication whenever it makes sense. Yeah, so what does it mean to say? So suppose that X is a metric space and E is a subset of X, and suppose that f and g are functions from E into the set of complex numbers. Yeah, so these are complex valued functions on the set E. Yeah, so much like, you know, R2, you can give the Euclidean metric on the set of complex numbers also. So this is a metric space, And let's consider a limit point of the set E. So P be a limit point of the set E, and suppose that limit of the function f at the point P exists and equals Q. So let me call it Q1, and the limit of the function G at the point P exists and equals Q2. Yeah. So what are Q1, Q2? Suppose that Q1, Q2 are complex numbers such that, yeah, so instead of considering a generic metric space Y, we have the set of complex numbers here. That's also a metric space. You can do the Euclidean metric there. Yeah. Okay, so then the following statements hold true. So I'm looking at the sum. So this is another function, f plus g. Yeah, so let me write this in this manner. So f plus g is defined on E. So limit exists and equals Q1 plus Q2. Yeah, so this is again saying limit of the sum equals sum of the limits provided the limit exists. So limit of the function fg, this is the multiplication. So this is the product of limits. So limit of the product is product of the limits provided the limit exists. And the third is the quotient. Looking at the function f by g, this is the quotient q1 by q2 provided it makes sense, which means that q2 is different from 0. Yeah? So limit of the quotient is quotient of the limits provided the limit exists, and is the second limit is different from 0. Is that okay? See, now that we have fixed the sequential criteria, characterization of limit of a function in terms of sequences, all of these statements 1, 2, and 3 can be borrowed from similar statements that were done for sequences, right? So we will skip the proof here, and I believe everybody can fix the proofs. Is that okay? Is there even one student who is a bit lost? Please ask. So does this make sense to everybody present here?
Yes, ma'am.
Yes? Okay. All right. Okay. So in that case, having defined limits of a function, we are now in a good shape to talk about continuous functions. Continuous functions between two metric spaces. So a function f from x to y, from one metric space x to another metric space y, when do we say such a function is continuous? Yeah. So we say that the function is continuous if it is continuous at each point of x. So we first turn to the definition of continuity at a point. So let me sort of discuss it in little more generality. Definition. So as before, given two metric spaces x and y, and let E be a subset of x and f is a function from E into y. Let's consider a point of E. Please contrast this with the definition of limit of the function f at the point P. The point P was or it can be possibly outside the set E. But in order to consider the continuity of the function f at the point P, the function f has to be defined at the point P. So P is a point in the set E. So then we say that f is continuous at P if for every positive epsilon there exists a delta such that what happens? Such that so let me sort of draw a picture here first. So I have E, which is subset of x, and f, which is a function from E to y. Again, I'll try to draw a picture in R2, assuming both x and y are R2 with the Euclidean metric. So this is the point P. F of P is some point of y. So you give me an epsilon, and I'm going to look at epsilon neighborhood of the point f of P with respect to the metric on y. So which means this, corresponding to this epsilon, there is a delta such that all the points in this delta neighborhood of the point P are mapped via f into epsilon neighborhood of the point f of P. As before, if for every epsilon I can find a delta such that all the points in epsilon neighborhood of the point P are mapped via f into epsilon neighborhood of the point f of P, we say that the function f is continuous at the point P. So which means that how do we write this analytically? We write it in the following form. We say that so f of x is in epsilon neighborhood of the point f of P, which means that the distance with respect to the metric on y between f of x and f of P is at most epsilon whenever x belongs to E and the distance between x and P is less than delta. This is exactly saying that x is in the delta neighborhood of the point P. And I want this extra condition that x has to be in E. Why? Because if x is outside E, the function f is only defined on the set E. So in order for f of x to be defined, we better restrict our attention only to the set E and not outside it. Yeah. So this is exactly saying what I have written in red, exactly saying the following, right? You look at the delta neighborhood of the point P, right? I am dropping this, the metric thing here just to sort of make the notation easy. Yeah. Then all points of this delta neighborhood which are in the set E are mapped via F into epsilon neighborhood of the point f of P. Yeah, which means that in the picture I have drawn here, so this is this delta neighborhood of the point P, and let's say this is my set E. Yeah, so this is, let's say, my set E in green ink. Yeah, this is my set E. So if I look at the delta neighborhood of the point P intersect with the set E, then this blue region is mapped via F somewhere inside this what color should I say, this pink disk. Yeah, so this blue region is somewhere here. Is that okay? Does it make sense to everybody present here? And when this happens for every choice of epsilon, then we say that the function f is continuous at the point P. Yeah. So if you're more comfortable with the real line, I will also draw a picture in the real line. So assuming, so E is a subset of X, right? So assuming X and Y are the real line with the Euclidean metric, what would the picture look like? You look at the point P on the real line and look at its image f of P. Yeah? And look at an epsilon neighborhood of f of P. So this is the point fp plus epsilon. This is the point fp minus epsilon. Corresponding to this epsilon, there is a delta such that, now let me draw E, E in this picture. So maybe we set E is, let's say, this. Yeah, so let's say E is this. So this is E in green ink. So E has to contain the point P. And let's say E is this. Yeah. All the points of the set E intersect with this interval around the point P are mapped via F into this epsilon neighborhood around the point P, around the point f of P. And if that happens, so this means all the points from here to here and here to here are mapped somewhere here. And if that happens for every choice of positive epsilon, we say that f is continuous at the point P. So is this okay? Maybe I'll go back to the definition. Is this okay with everybody present here?
Yes.
Yes. Okay. Yeah. So please note that I'm just saying it at the cost of repetition, that f has to be defined at the point P in be be continuous at the point P. Yeah? So much like the concept of limit, there is an equivalent criteria for continuity at a point also in terms of sequences. Let me state that next. So theorem, suppose that x and y are metric spaces. And let E be a subset of X and F be a function from E defined on E into Y. Let P be a point of E, then F is continuous at P in the sense of the definition given above, if and only if and only if for every sequence an in the set E converging to the point P, the corresponding sequence f of an, which is a sequence of points in Y, this is convergent and converges to f of P. Right. So this is a characterization of continuity in terms of sequences. Yeah, you might be sort of. So this is saying that limit of f of an as n tends to infinity equals. So you take the limit of the sequence an first, which is P, and then apply f, right? So one can interchange the order here. Whether you take the limits first or whether you apply the function f does not matter as long as you are working with continuous functions. Yeah. So again, let me draw a picture here. Again, something in R2. So if you have E subset of X, a function f, you have a point P, you have the image f of P. Sorry, you have f of P. Now, what do? What are we doing here? Yeah. No matter what sequence an you consider in you consider in E. Yeah, I want f of an to be defined, so that is why I would look at sequences only in the set E, converging to the point P. The corresponding sequence f of an must converge to the point P. And if this happens for every sequence of points in E converging to P, we say that the limit of the function f exists and equals f of P. That means that the function is continuous at the point P. Is this okay?
Yes, ma'am.
Yes. So I will, we did this in terms of limits in all its gory details when we were discussing limit of a function. So I will skip the proof here because it's much the same. Yeah, and I hope you will be able to fill in the argument here. I will instead talk about an example to illustrate what is this theorem saying. Yeah. So let's do that example. Let's consider a concrete function and let's apply this theorem. So let's consider, let's start with a very simple example on the real line with the Euclidean meter. So let's take f to be the function. Yeah, so E is the entire real line in this example. And I'm working with, so X is also the real line with the Euclidean metric, and so is the set Y. And let's consider the function as follows. So let f be given by, so how am I defining the function f? So f is 1 if x is rational or 0 otherwise. Yeah, so this is the indicator function for rationals. And we are required to investigate the continuity of f at each point of the real line. So let's use this sequential characterization of continuity, and let's try to investigate continuity of f. Right? Would somebody like to help me? Okay, so let me sort of give you the starting point. So let's start with a point x naught in Q, and so I'm going to investigate whether or not the function f is continuous at the point x naught. Yeah. So what is it I should do? I should look at all possible sequences of points converging to the point x naught. Correct? Is that okay? And then, yes, and then you look at the image sequence, right? And then that image sequence is either 1 or 0, depending on whether this sequence had rational or irrational points, right? So it is much wiser to do the following. Yeah. So let me do the following. So pick a sequence of points such that each of these points, each of xn's is not rational, such that xn converges to x naught. Can I always do that? Can I always find a sequence? So given a rational number x naught, can I always find a sequence of, so the set R minus Q, we have not introduced this in this course, is the set of irrational numbers. Perhaps you're already familiar with it. So can I always find a sequence of irrational numbers converging to Q naught? Why is this the case? Somebody would help me on this, clarify this.
By density property.
When their density property, exactly. So can you just tell me the statement exactly?
Ma'am, the irrational numbers is dense in R.
Right. So this is correct. So that's exactly why it's using. Yeah. So I'm using the one of the problems from the practice problem sheet that was handed out to you. So one of the exercises was following. Yeah. So you look at the set of irrational numbers this is dense in the set of R, yeah, which means that, so let me just not use this shorthand notation, but rather write it clearly, so that maybe you are tempted to solve some of the practice problems if you have already not done that. So use the fact that the set of irrational numbers are dense on the real line. Yeah, which means that given any real number, you can always find a sequence of irrational numbers converging to that real number, in particular for the point x naught, right? Now, what is the advantage of considering such a sequence? The advantage is the following, yeah. Now look at f of x naught, yeah. Now f of x naught, by the definition of the function f is 1, right? Because x naught is a rational number, but each xn is not rational. So which means that f of xn is going to be 0 for each n, right? Which in particular implies that the sequence fxn does not converge to the sequence fx naught. So what does it tell you about the function f at the point x naught? In terms of the theorem that we just discussed, this says that the function f fails to be continuous at the point x naught. Is that okay? And moreover, since x naught was any arbitrary rational number, this says that the function f fails to be continuous at each rational point. Is everybody with me? Yes. Now let's look at a point which is not rational. Yeah, you can essentially repeat the same argument. Let's look at a point, this. Yeah. So much like the previous case, you pick a sequence of points, this time of rational numbers, such that the sequence yn converges to y naught. Again, I'm using the fact that I'll just sort of leave it for you to figure out, but I'm using the fact that the set of rational numbers is dense on the real line. Yeah, so I'll put a question mark here. So the way the function f is defined, what happens to f at the point y naught? At the point y naught, since y naught is not rational, f takes the value 0. But what happens to f at each of yns? At yns, since each of these yns are rational, f is 1. Again, using the characterization of continuity in terms of sequences, it follows that the function f fails to be continuous at y naught. Yeah, so why is this the case? Here I have a sequence of rational numbers yn converging to y naught such that the corresponding image sequence f of yn does not converge to f of y naught. So f is not continuous at y naught. And since y naught was any arbitrary irrational number, F fails to be continuous at every irrational number. Conclusion, F fails to be continuous at each point of its domain. Is everybody with me?
Yes, madam.
Yes? All right. So we have defined a continuity at a point. When do we say a function is continuous on a set? If it's continuous at each point of that set. Yeah. So let me write that down. So again, you know, x and y are metric spaces. Here I'm not writing it, but continuing with the same notation, a function from x to y is said to be continuous on x if it is continuous at each point of x. Yeah. So the previous theorem said that if f from x to y is continuous, this can happen if and only if f of an converges to f of p for every sequence an in x converging to p. Yeah, so let me sort of, this might be too much to absorb orally, so let me at least draw a picture. So x is here, y is here, p is a point here, and f of p is here, right? So for every sequence in x converging to the point P, the corresponding sequence f of an converges to the point f of P. Yeah? And this happens for each point in the set x, then the function f is said to be continuous. There is an equivalent criteria of continuity in terms of open sets. Which is very, very useful, as we will see a little later. So what I'll do is, in the interest of time, I'll just state that result and we will see that next time. Yeah. So let me just state that. So theorem, so let x and y be metric spaces. And let f be a function from x into y. Then f is continuous on x if and only if f inverse u is open in X for every open set u in Y.